indirect utility function. This is the last thing we learned this week. So usually, as we have seen, we can solve the first order conditions for the optimal values of the goods and also the lambda. We haven't done that yet, but in principle, you can also solve lambda as a function of prices and income, just as the other Marshallian demand functions. Now, we will do it in a minute. And then, having solved all these Marshallian demand functions, it's possible to plug in this function of the quantity in the original functional form of utility function to arrive in something called indirect utility function. So that is the maximum utility that you could achieve written as a function of P's, the prices, and incomes, because remember we have solved, for example, x1 starts as a function of P1, P2, Pn, right? And income. So we plug this function inside the utility function, and then we get something called indirect utility function. So for that reason, you see that the optimal level of utility will depend indirectly on prices and income. So now let's again come back to the Cobb-Douglas utility function and do one example for the indirect utility function. So we already know that this is the functional form, but we have solved for the Marshallian demand function. Let's rewrite it again, which is x1 start equal A2 divided by P1 times I, right? And x2 start is 1 minus A over P2 times I. Now, the idea of indirect utility functions is that we plug these x1 start and x2 start into the original functional form of the utility function. So that would be, now we denote it indirect. We'll move it further. Indirect utility function, which now we denote as V. Which let's leave it there, equal use, where we plug x1 start, x2 start into the function, into this one, right? Let's see, what is that? Equals, so x1 to the power of A, so this term A over P1 times I to the power of A. And then let's have a square bracket over here instead, because that will be necessary. 1 minus A over P2 times I, everything to the power of 1 minus A. There we go. And now we can simplify everything. Now, but let's write everything in, rearrange it a bit. So we have A over P1 to the power of A. And then 1 minus A over P2 to the power of 1 minus A. And what else? Y, I, right? So I to the power of A times I to the power of 1 minus A. What happened over there? So the exponential will be A plus 1 minus A equal 1. So at the end you have I, right, to the power of 1, meaning I itself. Let's rewrite thing over here. So that should be now the indirect utility function is a function of prices and income, right? So it should be P1, P2, and I. So utility indirectly depends on the prices and income, just like the Marshallian demand function. So one last slide for this week related to the indirect functions that we just said is about the interpretation of the Lagrange multiplier, the lambda over here. Now, so once we have solved for x1 and x2, it's maximized utility maximizing level as function of income and prices. Technically, like with the utility function, we could also have the indirect Lagrange function, right? By plug in this Marshallian demand function and the optimum lambda function in the Lagrange function. Okay, and then by enveloped theorem, we could take the partial derivative of the Lagrange function with respect to income. What would it give us here is the only place you have income over there. And if you take the partial derivative of L with respect to I, you get the lambda, right? And what is envelope theorems? So I have uploaded also some material about this theorem on eCampus. Please check it out. But in general, envelope theorem is concerned with how the optimal value for a function change when the parameter of the function changes, right? Before that, we always think about the variables like x, the quantity, and we treated other parameters like prices, income as given. And now we would be interested to know, okay, how this optimal value changes when the parameter changes. And in such case, the envelope theorems is convenient because it said that we could hold the value of these variables, sorry. So we could hold the value of these variables at its optimum level that we have solved, like at a certain optimum level. We keep them constant over there. And then we take the derivative of the objective function, the Lagrange function, with respect to I, treated I now as variable, while keeping x1 and x2 constant at its optimum value. And then we arrive at lambda. So writing it this way, you can see that the lambda is the marginal utility of income. So it tells you how much more utility you will get when you have one more unit of income. Doesn't matter on which good this income is spent. And that's the interpretation of the lambda, the Lagrange multiplier. So now let's try deriving the function lambda start for the case of the Kaptaless function. So deriving the optimum lambda, which is lambda star. Now, from our CD utility, from our first order condition, we already got that A times x1 a minus 1 and times x2 1 minus a equal lambda p1. So this is the first equation in the first order condition. Now let's write this again. Use x1 x2 equals x1 to the power of a and x2 to the power of 1 minus a. That's it. So now we already solved for Marshallian demand function. Which is x1 start equals a times I over P1 and x2 start equals 1 minus a I over P2, right? So we plug x1 start and x2 start into the first equation over there. We would obtain a times a I over p1 to the power of a minus 1 times, let's have a square bracket over here, 1 minus a times I over P2. Everything to the power of 1 minus a equal lambda P1. Right? Now we could divide both sides by P1 to solve for lambda and then simplify everything. So that is lambda would be equal to a divided by P1, but in this case for simplification I would write it P1 to the power of minus 1. Nah? And then I have a to the power of a minus 1. I have I to the power of a minus 1. I have P1 again to the power of minus of a minus 1, which is 1 minus a, right? And then I have 1 minus a to the power of 1 minus a. I have I to the power of 1 minus a. And I have P2 to the power of minus minus of 1 minus a is a minus 1. Huh? And I can simplify everything at the end, which is, okay, a here. And then you have a to the power of 1, so to say, times a to the power of a minus 1. So at the end you have a to the power of a. The minus 1 cancel out with the 1 over here. Next thing, let's go with the exponent first. So 1 minus a to the power of 1 minus a remain the same. There's nothing to simplify. Now it comes I to the power of a minus 1 times here 1 minus a. Open the box again so that the exponent would be a minus 1 plus 1 minus a, which is 0. So I to the power of 0, which is 1. We don't have to write it out there. So it comes to P1 minus 1 plus 1 minus a. So that is P1 to the power of minus a. And times P2 to the power of a minus 1. Remain the same. And this is the solution for the lambda, if we want to solve it for the maximization.